Last time, then, we started looking at open and closed balls in d-dimensional space, where the open balls excluded those points that were distance exactly equal to the radius from the center. So you had strictly less than r there. For the closed ball, you had less than or equal r, so the points sort of on the boundary of your ball were included in the ball. I drew you a couple of pictures in 2 dimensions for the closed ball with the boundary included, with the open ball, which was a disc with the boundary circle excluded. And then we had a look in 1 dimension regarding r to the 1 as being the same thing as the real numbers. And I was asked a very good question about what is the difference between norm and modulus. And for a real number, because you're in r to the 1, the norm and the modulus come out to be the same thing. But usually, when we see 2 lines, and I call it norm, that means because we're working with vectors. And it's only because we're working the real line here that it comes out as the same as modulus. I reserve the single line modulus for real numbers in this module. So if you find you're using single line modulus for vectors, then something has gone wrong. And if you find you're using double line for real numbers, then it's possible that something's gone wrong unless you really are working in one-dimensional space. I think I'll add that to the module frequently asked questions document because it's actually quite a good one, and I have had it several times before. So in the real line, the open balls are just intervals. So an open ball is an open interval centered on the point x. The length is 2r because it goes r either side, which corresponds to the diameter is 2r. If you think of the diameter of a disk of radius r being 2r, where you think of the diameter of this interval as being 2r, diameter will come into the module later. And the closed ball then is the closed interval, and you can sketch that. And that brings us then on to the discussion of bounded sets and unbounded sets with the unfortunate clash that you get with the notation and terminology in vector calculus. But it just can't be helped because the notion of a closed surface is very old in the literature, and it just doesn't happen to correspond to the notion of closed that's also very old and used in this module and in other analysis modules. So our first examples of bounded sets are going to be just the open and closed balls that we've already met. They're going to be examples of bounded sets. Unbounded sets are going to be things like sets with infinite extent, boundless sets, sets that go off to infinity in some direction or other, or along some weird curve, or along some sequence of points. And bounded will be the opposite. Bounded means you can find some way of enclosing it in some big ball of finite radius. Well, those of you who've been to the session on why do we do proofs will know that definitions are really important. Here's the definition we're going to use in this module. But there are lots of equivalent formulations that do give you the same meaning. For that, we'll mention some of those. Some of them are on the question sheet. You should really have a good look at this definition, a look at the examples, at the questions on the question sheets. See if you can figure out why these things mean the same with each other. Understand why some examples are bounded, why they aren't bounded. It's a relatively easy concept. Some of you will find this chapter easier than later chapters in the module. But as I said, when it comes to the exam, if you ask questions about is this set bounded or not, this is the concept where I get the most wrong answers. So make sure you really do know whether sets are bounded or not. So a set's bounded if you can find at least one big positive real number r so that the whole set fits inside a big closed ball with that radius. Now, I've added those adjectives, but they're not part of the definition. But that's how you should be thinking about it. Because what you're saying here is that there should be a real number r that's big enough that the whole set S will fit inside that closed ball. If you find one real number r that works, then any bigger real number r will work as well. So as soon as you've found one, then you know there's going to be infinitely many. So the question is, are there any at all? If there are, then there's going to be infinitely many. Another way of saying it is then that all of the points in S should be distance at most capital R from the origin, or if you want to think of them as vectors or whatever, everything in S should have norm at most equal to capital R. And that capital R mustn't depend on which point you look at, otherwise it would be silly. If you could let R be 1 plus the norm of X, then of course you could always do it, and everything would be bounded. You can't do that. You need one positive real number R that works simultaneously for all of the X in the set. If it's not bounded, then we'll say it's unbounded. So I don't care whether you say unbounded or not bounded, they mean the same thing. So let's draw a typical picture. Most of my pictures will be two-dimensional because drawing three-dimensionally is harder and drawing four-dimensionally is even harder than that. So let me draw a little set. Let me have the origin here. And suppose I think I might have found a bounded set S. Well, if it's really bounded, that's because it will fit inside some closed ball of big positive radius. And so it'll look something like this. Again, I apologize for any distortion in the circle that you get. Unfortunately, the tablet screen I've got is widescreen, which means that when I draw a circle, it gets slightly stretched vertically for you. So you'll have to use your imagination that this is supposed to be a circle. Of course, that's what it looks like in 2 dimensions exactly. You take a bounded set in 2 dimensions, well, okay, we don't know exactly what shape it is, but there would have to be a big disk centered on the origin which you could fit the whole set inside. If you go up to 3 dimensions, you're talking about a big sphere, or a big solid ball, spherical ball, which has to include all of the points of S. Move up to higher dimensions still, and you're talking about these sort of circular hyperellipsoids. I'm not sure what the correct term is. Hyperballs, anyway. So if you can find such an R, then it's bounded. If you can't find such an R, it's unbounded. And as I said, the first examples of things that definitely are bounded are the balls themselves that we've already met. I'll start by looking at the balls that are centered on the origin. I want to prove that every ball centered on the origin is bounded. As we're going to discover in the how do we do proofs, to prove that every ball centered on the origin is bounded, we should take a prototype. So we just assume we've got one, and then we prove it's bounded. Now, this is particularly trivial in this case. So let little r greater than 0, and we show in a rather trivial way that both the open ball and the closed ball centered on the origin radius little r are bounded. I remind you again, if I say let little r greater than 0, that it's implicit that r is not infinity. We're talking about a positive real number r, if I say that, but it'll take ages if I wrote that every time. So I don't want to say let r be a positive real number, or strictly positive real number. I'll just write let r greater than 0. That's the convention. Because I said let r greater than 0, if I can prove this claim, since all I've assumed is r greater than 0, it will simultaneously prove it for all r at the same time. So I've done it for every ball. And that's how you prove something true for every ball. You assume you've got one, prove something about it, And since all you assumed was that you had a typical ball, you haven't made any additional assumptions, so what you've proved must be true for every ball, as we'll see again in the how do we do proof sessions. So we've got to find a big positive number, capital R, big enough so that these sets are contained in the closed ball. Well, obviously, take capital R equal little r, or you could take r plus 1, or any appropriate value, it doesn't matter. Once you've found one that works, bigger ones work as well. Then you've got the open ball is contained in the closed ball radius. So the open ball radius little r is contained in the closed ball radius little r. It's contained in this big ball, closed ball radius capital R, where you just made sure that capital R was big enough, for example, equal to little r, or anything bigger, doesn't matter, but as long as you specify something sensible that works, you'll be okay. And that shows that both the open ball and the closed ball are bounded at the same time. Remember, our definition of bounded is that you should be a subset of some big closed ball of positive radius. Both of these sets are. They're both contained in the big ball of radius capital R, so we're okay. Okay, but what if you move away from the origin as your center? We claim that all open and closed balls in R are bounded, even if they're not centered on the origin. So let's do the usual thing. As I said, you've got to take a prototype. You take any point x in R to the D and any positive real number little r. We've got to prove that both of these sets, the closed ball and the open ball, are bounded. And again, if you prove it for one, you prove it for the other. Let me prove that the closed ball is bounded, because the fact that the open ball is bounded will follow from that. The same proof will work for the open ball centered on x radius r. What's our strategy? My strategy is I'm going to draw a diagram showing you what looks like it's going on, but the diagram won't counter the proof. The diagram will look very convincing, and the diagram will show you how to find the proof. But because diagrams can be used to give convincing proofs if you know exactly what your set is in 2 or 3 dimensions. If you're working in d-dimensional space, then a diagram that's drawn in 2 dimensions is unlikely to be convincing enough on its own. But it may well show you exactly what's going on, and that's what we're going to do. So we're going to draw a diagram and then use it to help us find a proof. So we start with a 2D diagram suggesting why the result is true. And then we produce a general proof that works in d dimensions and isn't based on the diagram. It's based on the diagram, but doesn't rely on the diagram giving you, doesn't assume that things that work in 2 dimensions work in d dimensions. So we're going to write a formal proof valid in d dimensions, or d-dimensional space. So we'll sketch the closed ball, radius r centered on x, and put the origin somewhere. And I'll remind you, we've got to prove that that ball is contained in some big ball centered on the origin. It's unlikely to have the same radius as the small ball. So let's have a picture. So here then is the origin. And here is your ball. Here's your point x, and your ball, closed ball, centered on x, radius little r. I'll observe that the distance between 0 and x is norm of x. And what I want you to think about for a couple of minutes is how big a ball do you think I'm going to need, centered on the origin, to be sure that I've got the whole of that smaller ball in it? So I've got this small ball, radius little r, centered on x, and I'm trying to find a big enough capital R so that the big ball centered on the origin, radius capital R, is big enough to sort of swallow that whole small ball inside it. And the question is, how big does R have to be? Well, all you need to do is ensure that capital R is big enough, because once you've found one value that works, anything bigger works as well. So I'll give you a couple of minutes to talk amongst yourselves, just to convince yourselves that you know what's going on here. It's a two-dimensional picture, and you can think two-dimensionally if you like, and you'll get the right answer. So I'll pause the recording here. Okay, so let's find out how people got on. Thanks for pointing out that I left out the line, because I was going to prove the closed ball is bounded, so I should have had a line over my B here. It should be the closed ball centered on little x, radius little r. Not that it changes the calculations very much, but nevertheless, that's what I said I was doing, that's what I should be doing. How big must R be? Well, I think everybody has figured out that R should be at least as big as the norm of x plus little r. So you're allowed to take capital R equal to norm x plus little r, and that will show it's bounded, or you can take anything bigger, and that will show it's bounded, as long as you can write a convincing proof that the little ball is contained in the big ball in that case. Now, the picture makes it obvious in 2 dimensions, and obviously that's going to be a cross-section of the picture in 3 dimensions, and it's going to give you a valid picture in 3 dimensions. And I suppose you could argue that in higher dimensions, you only have to look at 2-dimensional cross-sections, maybe. But I would usually say that just because you've got a 2-dimensional picture that looks convincing doesn't necessarily mean you've got the right answer in higher dimensions. Things that are true in 2 dimensions aren't always true in higher dimensions. So let's write a proof so that there can be no dispute about it that works in d dimensions. So we'll set R equal to norm x plus little r, and we'll prove working in d-dimensional space, that BR of x really is contained in B big R of the origin. To do that, you have to prove that every point of the first set is in the second set. So we've got to prove that every y in the first set is also in the second set. To prove that every y in the first set is in the second set, we say let y be in the first set. Once we've done this, all we said was let y be in the first set, and we show it's in the second set. That will then tell us, since that's all we assumed about y, that will mean it's true for all such y. That will mean the first set is contained in the second set, which is what we're after. A subset of. Okay. Of course, to say that y is in this closed ball I want. I keep losing my bars. Everywhere I'm losing my bars. Of course, to be in the ball, radius capital R, centers on the origin, closed ball, that's, I can say, i.e., that the norm of y is less equal to capital R, because that's all that means. If you look at the definition of the closed ball centers on the origin, it just means that you have to have norm less or equal to that radius. Well, we have to use our definitions. Y in B R of x. So, norm of y minus x is smaller or equal to little r. And now we just estimate the norm of y. We write y as a sum of two things, which is what you get from the picture, really. So it's our standard trick. Norm of y, well, we want to use the fact that y is close to x and that we know something about the norm of x. That's equal to the norm of y minus x plus x. I haven't done anything yet. I've just rewritten it as something which is going to tell us about the distance to x, and then something about that's going to tell us about the norm of x. It's our standard trick when we want to do something with the triangle ball. That is less or equal to norm of y minus x plus norm x by the triangle law, or by the triangle inequality. And that's less equal to r plus norm x little r plus norm x. Because we know the norm of y minus x is less equal to r, we noted that above. We're just using our definitions here. And that was our choice of capital R. And so we've proved the result. So we've done it. That was a little proof of an intuitively obvious result. I've lost a bar. That worked in 2 dimensions, but our proof didn't assume we're in 2 dimensions. That was a d-dimensional proof using the triangle law for norm in d dimensions, And so there's now no disputing it. It works whichever dimension you work in. So here are a couple of ones that can give problems. Well, the first one particularly. How do you decide whether the empty set is contained in something or not? Is the empty set a subset of another set or not? People have asked me about this in second year and in third year, and it gives no end of trouble, in fact. But actually, you could argue it's a convention, but I think it's a bit more than that. That for any set you like, the empty set is always a subset of it. So, for all sets A, we have the empty set is a subset of A. The empty set is often problematic. One way to think about it is, what does it mean to not be a subset of something? To fail to be a subset of something means you have to have at least one point outside it. And the empty set can't do that. So I invite you to think a little bit about why the empty set is a subset of every set. Exercise. Think about this, in case you haven't already done so. What does B not a subset of A mean? As I've said verbally, it means there's at least one point in B that's not in A. The empty set can't do that because it hasn't got any points. So that makes the empty set particularly easy. It doesn't matter which radius ball you take, it always works. So in particular, the empty set is contained in the unit ball. So the empty set is bounded. The fact that R to the D is unbounded is because you can go off to infinity along any of the axes, for example, or indeed in any direction. So there's no chance of fitting the whole of R to the D inside one big ball. If you wanted to prove it, you have to do a bit more work, but I'll leave that as an exercise. If you can't figure out how to write out a proper proof of that now, then it'll become pretty obvious from lots of other ways we look at bounded and unbounded that are coming up. But if after we've done this chapter on boundedness you're still not sure about R to the D, then you're welcome to ask me and I can tidy that one up for you. This is on a question sheet, so we won't do it in full here, but I'll just sketch it. If you've got a bounded set and you look at any of its subsets, I claim they're bounded too. So say B is bounded and A is contained in B, then you're going to have a picture like this. And this is not a formal proof, as usual. You've got B is contained in some big ball. So you'll have the origin here. You'll have your set B. And there'll be some big ball oh, this machine is giving me trouble today. There'll be some big ball, big enough, include all of those points. So this big ball is not to be confused with the set B. Perhaps I should use a different letter. That capital B set is nothing to do with ball. Okay? Inside that B, I've got some other set called A. And it should now be obvious that the same ball that works for B works for A as well. So once you've found a big ball that works for B, it's going to work for anything that's inside B, like some smaller set A. And it's an exercise to fill in the details properly. See the question sheet. Fill in the formal details. Which gives you a bit of practice in writing a formal proof that's not too hard. Now, if you're in one dimension, then you already had last year a notion of bounded below and bounded above. So be warned that bounded below and bounded above doesn't make sense in higher dimensions, at least not in any obvious sense. If you are going to start talking about sets in d-dimensional space being bounded below and bounded above, you better explain what you mean, because it's not a standard notion. But in one dimension, there's the notion of bounded below and bounded above, and if your set is bounded below and bounded above, then you can fit it into some nice interval, and you get the notion of a bounded set. So perhaps you should say a non-empty set, but I think it would be better if S was non-empty here. The empty set is bounded anyway, so you only have to consider non-empty sets. And a non-empty set is bounded if and only if it's bounded above and bounded below. I think the empty set probably works as well, because everything is an upper bound for the empty set and everything is a lower bound, so it's okay. But it's perhaps a special case. A bounded set need not include its boundary. Bounded and boundary really have no connection with each other at all. They may sound similar, but there's almost no connection between bounded and boundary. So do watch out for that. What's a typical bounded set which doesn't have its boundary? Something like an open ball. Here, the typical bounded set which doesn't include its boundary. The open unit ball, in any dimension you like, is bounded, but excludes its boundary. So just don't even think of them as being connected to each other, those two words. Just try to imagine they're completely different words. Or even make up your own word that doesn't sound like one of the other ones. Okay, we're going to be looking at some further important examples. And on the question sheets, there's a lot of other ways of thinking about whether sets are bounded or not. A set's bounded if and only if the set of all possible distances between pairs of points of S is bounded above. So you look at all the different pairs of points in the set, and you ask how far apart can they be. And now you're looking, instead of radius, you're sort of looking at diameter. What's the diameter of a set the diameter of a set is how far apart can 2 points in the set be. Well, you might not be able to get a maximum, but you might at least be able to say that they can't get further apart than a certain amount. And so you can talk about sets having finite diameter because no pair of points in the set is more than a certain distance apart. And it turns out that that's equivalent to being a bounded set, but it's a different way of thinking about it because the notion of boundedness we've had is sort of look at the distance from the origin and you look at one distance. This alternative way of thinking about it is you look at pairs of points and the distances between them in the set and ask if that's bounded above. Well, you can prove that they're equivalent. And in fact, most of the intuitive notions that you think of meaning something being bounded really will work. So there's a lot of questions on the question sheet for you to check that one up, but we won't go through the details here. So we leave that as an exercise. Now, if too many of these exercises give trouble, you can let me know. I can tidy them up, give you a bit more information about them. But I don't want to slow down too much at this point because there's harder material coming later. So let's keep moving. So a little bit of revision here about intervals. And then we'll move into the higher dimensional analog of intervals, which are the D cells, but they're just various kinds of rectangle, cuboid, hypercuboid, various different kinds of things you can get in higher dimensions that are made up by restricting the coordinates, each to lie in some particular interval. So if you take a pair of real numbers a and b, with a less than or equal to b, then there's 4 different kinds of bounded interval you can make. I'm not going to bother proving that these intervals are bounded. It's pretty obvious. You can check it for yourself. And anyway, it follows from some of the stuff we do later. So there's the standard closed interval, which we've mentioned already, those real numbers x that lie between a and b inclusive. And you can draw that on the real line, as we've done before, with some way of indicating that the endpoints are included. And then we've got our 2 different alternative notations for the open interval, either using backward square brackets or using round brackets to show that the endpoints are excluded, and we take those real numbers x, which are strictly between a and b. I don't mind which notation you use for open interval. I tend to find that the round brackets work better when you're sketching your interval on the real line, whereas the backward square brackets are useful if you're trying to avoid getting confused with a point of r squared. For example, a comma b could be a point in r squared with x coordinate a and y coordinate b. And there are situations in which both occur in the same statement. Not so much in this module, but in metric and topological spaces and other later modules, you will come across situations where you're dealing both with open intervals and points of r squared in the same sentence, even with the same pair of values, a and b, and so it really can get confusing. So it is useful to have the other notation available. And then there's 2 kinds of half-open interval. And if you use the term half-open, you really should only use it about intervals. Most subsets of the real line are not intervals. If you take something like q, the rational numbers, it's not an interval, doesn't count. You can't talk about q being open or closed or half open or anything like that. That would be nonsense. So we only do this for intervals. The half-open intervals then, between a and b, you exclude exactly one of the endpoints. And you could exclude either the endpoint a or the endpoint b. And there are your 2 half-open intervals. So you've got 4 kinds of interval when you're working in one dimension. And you can sketch those on the real line. But I won't bother with that. There's a degenerate interval. When a equals b, I accept the closed interval notation ab as what I call a single point set, which means it's only got a single point in it, the point a. So that's a degenerate interval. And some people count the empty set as an interval. I think a lot of people count the empty set as an interval. That's another degenerate interval. So they're not very interesting intervals, but you should know that they're possible. Normally we work with non-degenerate intervals. So this is a degenerate interval. As I said, most subsets are not intervals, like Q is not an interval. And neither is the complement of Q, the set of irrational numbers. That's R take away Q. And in fact, if you take a disjoint union of two intervals, it's not an interval either. If you take the union of 0, 1 with 3, 5, it's not an interval either. It's a union of two intervals. If they'd overlapped, or if they, in this case, if they touched, they would have gone together to make an interval. So that's one dimension. And now you move into R to the D, and we want to know what corresponds to intervals in R to the D. And actually, some authors call the generalized version, they still call them intervals, whereas other authors call them D cells. I'm going to stick to D cells just in case there's any worries about it. I don't think that many people call them intervals in R to the D, but you will find some authors who do. And I say you make Cartesian products. Now, if you remember how Cartesian products worked, it was nothing to do with multiplying real numbers. It was about restricting each of the coordinates separately. So if you want to take a Cartesian product of intervals, you're going to be saying the first coordinate has to lie in one interval, the second coordinate has to lie in some other interval, the third coordinate has to lie in a different interval, and so on all the way up to D. You specify which interval each of them lie in. And of course, in 2 dimensions, that means you'll be specifying some rectangle with some of the edges included and some of them excluded, possibly. In 3 dimensions, if you insist that each of the 3 coordinates lies in some particular interval or other, you'll be dealing with a cuboid, and so on. You move up to higher cuboids. So here are the intervals you're going to be specifying for the particular coordinates. There's going to be an A1 and a B1 to restrict the first coordinate, an A2 and a B2 to restrict the second coordinate, all the way up to AD and BD, which are going to restrict the dth coordinate. And corresponding to those, you've got closed intervals, open intervals, and, of course, half-open intervals available of 2 kinds. The closed D cell is taken by taking the Cartesian product of the closed intervals, A1, B1 up to AD, BD, which means that you allow each coordinate to lie between the corresponding A and B, inclusive. So it's those points x in R to the D, and remember that by default, if I don't see otherwise, x is equal to x1 up to xd here. So if I don't see otherwise, that's what the coordinates of x are. So it's those points x of R to the D. So the first coordinate is between A1 and B1 inclusive, all the way up to the dth coordinate will be between AD and BD inclusive. And then there's an open D cell where you say that they're all exclusive. This corresponds to the open intervals. So you take the product of the D open intervals. And again, this time, x1 is between A1 and B1 exclusive, and so on up to xd between AD and BD exclusive. So you've got closed D cells and open D cells. And then there's a whole load of sort of half open or possibly quarter open or fractionally open, in some sense, details as well. But we should sketch a few of these, which we'll do next.